So today I will derive the mirror equation. So it's an equation that describes how the image is formed in spherical mirrors. So if you know like where the object is placed and the size of the object, so if you know this distance here and the size of the object, with the mirror equation you can calculate where the image will be located if you know the focus, or if you know like the center, so the size of the mirror. If you know the size of the mirror and the information about the object, you can calculate exactly where the image will be and what's the size of the image. Okay, so how will we do this? First, we need to draw some notable rays. I like to use those two here. So the first one is the parallel ray. So if there's like a light ray coming from the tip of the object and it's reaching the mirror parallel to the principal axis, it will reflect, passing through the focal point. That's a characteristic from spherical concave mirrors. Okay, and the second light ray that I'll take is this one here, the ray that is reaching the vertex. It gets reflected back with the same angle. And why is that? Then you have to remember that if I like zoom in here and look just at this tiny region here, this tiny region behaves as if it was a plane mirror. And if you do remember the law of refraction, if you have a plane mirror here and there's like a light coming here, this light will get reflected with exactly the same angle. So this angle here, it's equal to this angle here, okay, in plane mirrors. And if we look at a small region, like this region here, if we just zoom in, it behaves as if it was a plane mirror, okay? So now it's just playing with trigonometry. I will take two triangles. So I'll take this triangle here, the first one, with this triangle here, okay? This triangle that I'll be drawing here. Oh. So I'll take this triangle here, okay? The second one that I'll be taking, I'll be using yellow. Oh, here, forgot to draw the image. So we know that the image will be formed where the light rays meet. So here is where the image will form. And the second triangle that I'll take is this one here, like this triangle here. So I'll just draw them here a little bit different so it's easier for us to see. Okay, so I have like a big triangle here. Draw the triangle here. We have like a big triangle here with a certain angle, theta here. This angle here, theta. And I have a small triangle, a smaller triangle. Let me see if I can pull a smaller triangle with the same angle here, okay? This angle here because of the loss of reflection. Okay, what are the sides of this triangle here? This size here, this size here, is the size of the image. So I'll use h for height, not image, from the object. So HO is this size here, the size of the object, right? And this distance here is the distance that the object is from the mirror. So, and this is the hypotenuse. We won't be using it, so but we can calculate it using Pythagoras theorem. For the second triangle down here, we know the height of the image and the distance that the image is from the mirror, okay? Those two triangles, if we look here, they have an angle theta. They are the same angle, and they have a 90-degree angle. So this angle here must be equal to this angle here. So if they have all the angles are the same, they are similar triangles. It means that the smaller triangle here is just a small and flipped version of this bigger triangle here. So they are the same triangle but scale at different scales, okay? So this one here is basically a scaled down version from the triangle up there. So what I'll do is I'll take the tangent of my angle, the theta angle, from both triangles, and since they are similar, if I take the tangent using this triangle here, the big one, it must be equal to the tangent if I take this triangle here, the smaller one. So that's what I would do. So the tangent is the opposite side divided by the adjacent side. So using this triangle here, the opposite is the height of the object and the adjacent is the distance of the object. So height of the object divided, theta here is O, divided by the distance of the object must be equal, now using this triangle here, okay? The height of the image is the opposite, the adjacent is the distance of the image, so height of the image divided by the distance of the image, okay? This equation here is the first important relationship. From here, we can take the magnification of the image. In that case, what's the factor that the image gets altered? So how do I do this? I basically, like, if I cross multiply, we'll get something like this. Height of the image, it's equal to the distance of the image divided by the distance of the object times the height of the object. How have I done this? Basically, I've just taken this one here and tossed to the other side. So multiply both sides by the distance of the image, okay? And now I have that the height of the image is this factor here times the height of the object. So what this factor means physically, it means how many times the image is the object. So if this number here, it's for example 2, it means that the height of the image is twice the height of the object. If this number here is for example a half, it means that the height of the image is equal to half the size of the object. So this factor here is how many times the image is bigger than the object. It can be, so if this number is between 0 and 1, the image is smaller than the object, and if this number here is larger than 1, it means that the height of the image gets bigger. In this case here, of course, that this factor will be a fraction because the image is way smaller. So we can see if the image it's bigger or smaller than the object by looking at this factor here, which is called the magnification factor, okay? So that's the first relationship. Second thing here is that the image is upside down. So to correct that, we just plug in a negative sign here just to indicate that the image is flipped upside down, okay? That's where this minus sign comes from. But so far, I just described what's the size of the image given the size of the object. So what's the size of the image given the size of the object? And this number here tells me how many times the image gets scaled according to the object. So now I will play a different game using different triangles. So I'll just draw here really quickly. Okay, so I'll just redraw. This is the same drawing, but I'll choose two different triangles to describe the distances that the object is from the mirror and the distance that the image is from the mirror. So far, we managed to describe the relationship between the heights or the sizes. Now we want to describe the relationship between these distances here, okay? So now I'll choose a different triangles. So we have this angle here, this different angle here. Let me use like yellow, can be this color here. So I have this angle here. This angle is exactly the same as this one here, okay? This angle here, I use theta already, I'll use alpha now. It's also equal to this alpha here. And we know this from geometry. If we have like two intersecting lines, this angle here is equal to this angle here, and this angle here is equal to this angle here. So opposite angles, when we have two lines crossing, they're always equal. So by this relationship, we can get that those two angles are the same. So now I'll take two triangles, two different ones. The first one will be this one here that I've used color yellow, and I'll use now this color here to take the second triangle, which will be this one here. Okay, just taking the triangles from the image. I'll draw these triangles here again, just so it's easier for us to see. So the first one, it's a triangle like this. Here I have the angle alpha. This height here, it's this height here, okay? And this height here is the same, if we look here, is the same as the height of the object. Height of the object, okay? And this side here, there, is this distance here, and this distance is equal to the focal point, okay, to the focal distance. So that's the first triangle. The second one, it's a triangle that is like this. First, I'm not drawing them up to perfect scale, okay, just so we can have a hang of it. Okay, and we have this angle here, which is also alpha. This side here, it's exactly the same as this side here. So it's the height of the image, okay, the height of the image. Now, it's a little bit more complicated because we want this side here, okay? But how can we calculate this side here? So let's look here. I'll use like purple, just let me choose a different color here. It could be this one, won't make a difference. So if I take this total distance here, that I've drawn, this total distance here is the distance that the image is from the mirror, okay? But we want just this little piece here. This little piece here is the distance of the image, which is the total distance, minus this here. But this here is the focal distance, so minus the focal distance. So this is the distance from the image minus the focal distance. Now we have two triangles we need, and again we'll relate them with the tangent of alpha, because since they have alpha and 90 degrees, they are similar triangles. That means that they are actually the same triangle, but this is just a scaled up version of the smaller triangle. Okay. So the tangent of alpha, in this case here, using this triangle, it's the first triangle here, is the opposite, height of the object, divided by f. It's equal to the height of the image, now using the smaller one, height of the image divided by the distance of the image minus the focal length. So what's the next step now? So we have everything, just need to cook a little bit the equations, to give a little bit of massage to the equations to get where we want. So I will combine this equation here with this equation here, okay? How will I do this? I will combine those two equations here, okay? But how? So from this, the first one here, I will use this relationship here, that the height of the object, the height of the object divided by the height of the image is equal to the distance of the object divided by the distance of the image. I've just cross multiply here, okay? Like switch places, okay? And then I'll get this one here, this relationship here, okay? So I'll use this relationship here from the first equation. And from this second equation, I will have, I'll do the same thing to throw this here and throw this there. So with the second equation, I have that the height of the object divided by the height of the image is equal to f divided by di minus f, okay? That's what I That's the relationship I've just got. So I'll compare those two equations. So can we see that these are equal? So this two must be also equal. So that's what I'll do. I'll take this relationship here, make them equal. So what I'll have is, let me just throw that down here, just so it's easier, okay, to see. So what I have is that the distance of the object divided by the distance of the image, it's equal to taking this here and making equal to this here down here. So it's equal to the focal length divided by distance of the image minus the focal length. Okay. If I invert both sides, so turn the fractions upside down per se, the O, distance of the image divided by the distance of the object. Remember, I'm just flipping the fractions, okay? The I minus F divided by F, okay? From this, I take that the I divided by the O is equal to the I divided by F minus F divided by F. What have I done here, right? I've just taken this fraction here and I've separated into two fractions. So if I sum these two fractions here, since they have the same number down here, I just like keep this number and do the sum, in this case the subtraction, upstairs. So I've just opened this fraction here. Why have I done this? Because here it's f divided by f, that's just 1. So I have that di divided by do. I'm just going really slow so you don't miss a step. Di over f minus 1, okay? Minus 1. I'm almost there now. So from here, what can I do is that I can take this di here and throw to the other side, dividing each term. So I'll be left with 1 over the distance of the object. It's equal to the I divided by the I times f minus 1 divided by di. And here you see that here cuts this di here cuts with the di downstairs. And finally, I'll write it down here. We'll have that 1 divided by do is equal to 1 divided by f minus 1 divided by di, okay? If I take this term here and throw to the other side, I'll be left with the most common way of writing this equation, which is like this: 1 over di is equal to 1 over the focal length. So that's the mirror equation. That's the final version. So now I can describe the relationship between the distances of the image and the object given the focal length. I can relate the distance of the object, distance of the image with the focal length, and with this equation here, I can relate the distances of the image and the object with the height of the object. So by knowing the focal length and the distances, I can fully describe the image with those two simple equations. Of course, that it took us a little bit of like work to get here, but now we can just apply those equations. Okay, we just have to be careful with the sign convention. So what's the sign convention? So sign convention for the focal length is that if the focus is at the same side as the light rays, there it's positive. So if it's a concave mirror, the focus is here, and it's the same side as the light rays, So it's the same side. So in this case here, the focus will treat with a positive sign. And if it's on the other side, on this case a convex mirror, the focus, it's a virtual focus, it will be around here, okay, focal point, and the light rays, like they're coming parallel, they will get reflected relative to the focal point. Of course, my drawings are really bad, but in this case here, we need to use the focal with a minus sign, focus with a minus sign. If we just stick to those rules, the sign rules, sign convention, and don't forget to put a minus sign here as well, then this equation should work for every type of mirror, every type of distances that you want. So, for example, if you plug in the equations and you have that the distance of the image is a negative sign, it means that it's on this side of the mirror. If it's positive sign, it means that it's on this side of the mirror. If it's the image, in the end, here, you have like a negative sign here, it means that the image is flipped upside down. So we're analyzing the signs, we can know if the image is on this side of the mirror, it's on this side of the mirror, if it's upside down or upside up. So we can know everything about the image by knowing the distances and the heights and the focal point. So if we know those informations, we are good to go. We can fully describe any image at any spherical mirrors.